let's say I was driving a car, and at each point in time, I want to graph the distance at that point in time. So I'm going to put on the x-axis t for time, and I'll use unit seconds. And then on the vertical axis, I'm going to put distance as a function of time. And I'll do that in units of meters. Let's say I started at 0 seconds at 0 meters, and in 1 second, I move 1 meter. And 2 seconds, I move 2 meters. Well, then it's pretty easy to see that the speed I'm traveling is 1 meter per second. But how do I solve that in general? Well, I can take one point in time, which I'll call t1, and the corresponding distance value would be d at t1, and another point in time, t2, which has distance d at t2. Now, if I want to find the speed, first let me see how much I'm changing in time. So this distance here is how much I've changed in time. And you can see that because this whole length from 0 to t2 is length t2, if I subtract this length t1, then I'll be left with this distance here. So this distance, which we call the change in t, equals t2 minus t1. Now this operator, which we denote by the Greek letter for capital D, delta, is the difference operator. It finds the difference between two numbers, t1 and t2, such that the change from going to t1 to t2 is denoted by this delta t. Similarly, this distance here between d at t1 and d at t2 would be delta d, which would equal d at t2 minus d at t1. So my speed, which I'm going to label v for velocity, would be the change in distance divided by the change in time. This is called a rate of change. And for a linear function, which is a function that makes a straight line, this is also known as the slope. And I can write this out as d at t2 minus d at t1 divided by t2 minus t1. Now I'm going to go ahead and write this a little bit differently. So we know that delta t is t2 minus t1, which means that t2 equals t1 plus delta t. So what I'm going to do is I'm going to let t1 equal just t by itself, and t2 will equal t plus delta t. Now I can write my speed, or my slope, a little bit differently, where I can write it as d at t2, which is t plus delta t, minus d at t divided by delta t. Now what if I had a curved function that isn't a straight line? So now I'm going to write this as f at x, and the horizontal axis will just be x. Well, if I pick 2 points like I did earlier and try to find the slope, that would be like finding the slope of the line connecting these 2 points, which would find the average slope between these 2 points. But that is not the actual slope, because as you can see, this line doesn't really line up with this graph in any way. So what can I do? Well, you might just notice, well, why don't you just pick the 2 points to be closer together? That way, the line will line up a little bit better. This is definitely better, but it's still not perfect. And the only way to get perfect is to find the instantaneous slope at each point. That would be to find the slope at 1 point and 1 point only. So the strategy to do this is when we pick our 2 points, we need them to get infinitely close together. And the way to do that is, instead of denoting this change here as delta x, we denote it as dx. This lowercase d, is called the differential operator, and is essentially the same as delta x in the limit that delta x gets closer and closer to 0. So this is, using this very, very, very small change, we are essentially finding the change that occurs at one point, since this dx is basically infinitely small. This is how we find the instantaneous rate of change. So now, if I just use this idea in our slope formula, then the rate of change in f at one point in x, which I'm going to denote as f prime at x, so f prime at x is our slope at each value of x, then instead of using the delta, we're going to use this d for an infinitesimal change, which I can write just as I did before as f at x plus dx now minus f at x all over dx. And if I write this again using our definition with that limit, it'll look something like this. This here is the definition of the derivative. So the derivative gives us the instantaneous rate of change at each value of x. So this is the derivative of f with respect to x, which, like I said before, we can also call f prime at x. So let's do an example. Let's take the function f at x equals mx plus b, which, as you probably know, is the ordinary equation of a line. So if I want to find the derivative, I take the limit as delta x approaches 0, and first I do f at x plus delta x. So where x is, I put x plus delta x. And then I subtract f at x, which is mx plus b, divided by delta x. This expression, if I expand it out, will look like this, so that I'm distributing that m inside the bracket. And you can see that this mx cancels with this mx, this b cancels with this b, and then you're just left with m delta x divided by delta x. Those two delta x's cancel, and you're just left with m. So this becomes the limit as delta x approaches 0 of m. And if you just plug in delta x equals 0, and delta x appears nowhere in this expression, so this would just become m. So the slope of a line is m, just as you would expect if you remember your early high school math. Now this whole if you don't understand what limits are, this whole thing with limits, basically at one point you're trying to plug in delta x equals 0, because delta x is approaching 0. But the problem is, if you just plug in delta x equals 0 right away, well then this will become 0, and this will be fx minus fx, so that'll cancel, that will be 0, and the bottom will also be 0. So you'll have something like 0 over 0, which is indeterminate. The reason it's indeterminate is because I can set this to equal any number m, and if I just multiply both sides by 0, I'll get 0 over 0, which is a true statement. So this 0 over 0 equaling some number is true, no matter what the number is. But what it means is the way that our expression is at the moment, it doesn't give us any useful answer. So when we deal with limits, we basically play around with this expression, usually trying to get things to cancel so that eventually you can plug in delta x equals 0 and get something useful. That's what we just did in this example here. So using the definition of the derivative, you can actually come up with several derivative properties. So I'm going to go ahead and write those derivative properties now. So let's say in this column we're going to have our function h of x, And in this column, we'll have the derivative of h of x. So this first property is called the constant product rule. Basically, if we have a constant times a function, the constant basically comes out, and you just take the derivative of the function by itself. This here is the sum and difference rule, where basically the derivative distributes into each term. Here we have the product rule, where if we have two functions being multiplied together, you take the derivative of the first function times the second function, plus the first function times the derivative of the second function. The next rule is the quotient rule, where if you have a function divided by another function, then the derivative is the derivative of the first times the second minus the first times derivative of the second divided by the second function squared. And the last rule, which I'd say is one of the most important rules, is the chain rule. That's where I have a function of a function. So now f is a function of g, and g is a function of x. So for the chain rule, the derivative is the derivative of f with respect to g times the derivative of g with respect to x. Now all of these rules I will prove in another video, and I'll prove them using the definition of the derivative, which is that expression we had involving limits. But for the chain rule, there's a really nice proof if you just understand what our notation is saying. If I have df of g of x by dx, I can write this a little bit nicer by just writing df by dx. And I can multiply the top and bottom by dg. And if I just switch these terms around, so this is, first of all, df dg by dx dg, I can just switch these terms around to show that this is the same as df by dg times dg by dx. And since f is a function of g, then this becomes very easy to do. Take the derivative of f with respect to g, and then take the derivative of g with respect to x. Now also with the definition of the derivative, or using the derivative properties that I've written here, you can find the derivative of several base functions. So in the left column, I'm going to put the function, and in the right column, I'm going to put the derivative of the function. So first, if we have a constant, then the derivative is 0. If we have a power function, which is x to the power of any number, any real number, then the derivative is n times x to the power of n minus 1. So you bring the exponent down and subtract 1 off the exponent. The derivative of an exponential function, some number a to the power of x, is a to the power of x times ln of x, where ln is the natural logarithm. If we have the exponential function written in terms of e, then the derivative is just e to the x, which you can get easily using the exponential function derivative if you just plug in a equals e. Now the inverse of the exponential function, log base a to the x, the derivative is 1 over x times ln of a. And finally, or not finally actually, the natural logarithm of x, the derivative is 1 over x. Now I'm going to write another column here where I'm going to do a bunch of trig functions, because there's several of them, and I'm not even going to write them all. I'm just going to do the 3 main trig functions and their inverses. So if I have sine of x, the derivative is cos of x. If I have cos of x, the derivative is negative sine of x. If I have tan x, the derivative is secant squared of x. If I have the inverse of sine, sine negative 1 of x, the derivative is 1 over square root of 1 minus x squared. The inverse of cos is the same thing as for sine, but with a negative. And the inverse of tan is 1 over 1 plus x squared. Again, in my proofs video, I'm going to prove all of these, all of the derivatives for these base functions. But for now, here they are. So knowing the derivatives of all these base functions and using the derivative rules or derivative properties, we can figure out the derivative of any function at all, basically. So let's do an example. Let's say I have sine of x squared. And I want to find the derivative of f. First of all, notice that this is a function of a function. We have sine of g, where g of x equals x squared. So that sine is a base function, and x to the power of a number, x to the power of 2, is also a base function. We have the sine base function and the power function. So we need to use the chain rule. So first we take the derivative of f with respect to g. So we take the derivative of sine with respect to g, which is cos of g, and g is x squared. Then we multiply that by the derivative of g with respect to x. So the derivative of x squared, you bring the exponent down and subtract 1 off the exponent. So that's going to be 2x. So our derivative is 2x times cos of x squared. Now, before I end off this video, let's look at how a derivative can be used to describe a function. So here I'm going to sketch out a function f of x. Let me just draw it like that. Now below it, I'm going to sketch out the derivative of that function, f prime at x. So first, let's take a look at the slopes. So over here, the slope is going up, it is positive. At the top, it's 0. And then it goes back to negative. Now if we look over here, this slope is negative. And then it comes over here and goes flat, it goes to 0. And then it goes to positive again. So if we line up what's going on here, when I draw the derivative of f prime at x, at this point the derivative is 0. On this side the slope is positive, so I have to draw it above 0. Over here it's negative, and then it goes back to positive again. So let's look at some of the properties that we notice here. On this side of f at x, the function is increasing. It has a positive slope, it's going up. This corresponds to the derivative being positive. So if f prime is positive, that means that f is increasing. Similarly, if f at x is going down, then the slope is negative. So f at x is decreasing when f prime is negative. So when f prime is below 0, it's negative. Then f is decreasing. And notice that where the derivatives are 0, over here we have a maximum in f. And on this side we have a minimum at f. The maxima and minima correspond to when f prime is 0. And if f prime is going from positive to negative, then we know that we're going up and then down, which means that that critical point, f prime equaling 0, corresponds to a maximum. Similarly, for the minimum, we're going from negative to positive, which means we're going down and then up, which means that minimum, or that critical point where f prime equals 0, we know would have to correspond to a minimum, because we go all the way down and then back up. Now we can take this a step further and describe it in terms of the derivative of the derivative, which is the second derivative of x, which I'll write as f double prime at x. So first, let's take a look. Over here, the slope is 0 of f prime. So just like before, f double prime will be 0 there. Over here, the slope is positive, so f double prime will be positive. And on this side, the slope is negative, so f double prime will be negative. So now look at this. Over here, we have the slope being positive on f, then going to 0, then going to negative. This corresponds with f prime being positive and then going negative. This means the slope on f prime is decreasing, or sorry, it's negative, which means f double prime is negative. So when f double prime is negative, this corresponds to f being concave down, because that means that f is going in this sort of direction, which means it is concave, pointing downwards. Similarly, for this side, we have a negative slope, and then we go to a positive slope, which means f prime is going from negative to positive, which means it is a positive slope. F prime has a positive slope, which means f double prime is positive, which corresponds to f being concave up, because f will be concave in the upward direction. So if I have a critical point where f prime is 0 and f double prime is negative, I know that this is a critical point when I have a function that's concave down, which means that critical point is a maximum. If I have another critical point where f prime is 0 and f double prime is positive, then that means I have a critical point which occurs when this is concave up, which means that critical point has to be a minimum. So that's how you can use the derivatives of a function to describe how the function is shaped and where the maxima and minima are, which is very important, as we'll see in future videos, in understanding the physics, especially in terms of motion and speed, which was the first example I gave in this video. So if I have some distance function, some function d of t, I can find the velocity at any point in time by finding the derivative with respect to t of the function d of t. Thanks for watching.